Welcome back to Math 210, Calculus 1. So we'll start off with an exercise to help us review on please find the extreme values. So let's look at this. There's two parts. I'll do one and I'll let you practice on the other one. So let's take f of x equals 2x squared minus 8x plus 7. And let's take the following question. So first of all, find the extreme values on 0, 5. Find the extreme values on the interval from 0 to 5. And what do we have to do this? So we've got this extreme value theorem that tells us that the extreme values, the absolute max and the min, occur either at endpoints or at critical points. So your first step should be to solve the equation 0 equals f prime of x in order to find those critical points. Remember, critical points are places where the derivative is 0 or it doesn't exist. And this is a quadratic. Its derivative exists at every point. And so what's going to be f prime of x? So this is for x minus 8. So it's this nice linear function, actually. It kind of makes things a little bit simpler. So I get 0 equals 4x minus 8. So 8 equals 4x. And x equals 2. So I can really just test these points. So I can test out the endpoints, 0 and 5. And I can test out this point, x equals 2, my critical point. So I literally just plug in the numbers in order to, in order to figure out which one's the biggest. And maybe I'll just use Desmos to do that. I don't want to do too much in front of you. Let's be civil. Let's take f of x equals 2x squared minus 8x plus 7. Let's take f of 0 is 7, f of 2 is -1, and f of 5 is 17. So 7, -1, 17. It's telling me that the maximum occurs at x equals 5 and is equal to 17. So the absolute maximum on the interval from 0 to 5 is 17. And the absolute minimum on that same interval is -1. And so here's the problem that I'll ask you. So please do the same thing, except I'm going to change the interval. So let's take extreme values on f equal to -4, on the interval from -4 to 1. So let's look at the interval from -4 to 1 with the same function. Please find the extreme values of f of x on that interval. So I'm going to give you a couple minutes to work on that, and then we'll come back and discuss. Okay, so after giving you some time to think, I'll discuss it as well. So like once again, extreme value theorem says that the absolute max and min over the interval from -4 to 1 can only occur at -4 or 1 or at a critical point. But you've figured out in part 1 that the only critical point was x equals 2. So that's not in this interval. So there's no critical point. So your only options are x equals -4 and x equals 1. So -4 and 1, and one of them's the maximum and one of them's the minimum. And again, let's use the software to get this. Here's the, I mean, this picture will be helpful too, but let's, first things first. So f of -4 is 71 and f of 1 is 1. Go fix my lighting. And so you can see the minimum value here is going to be 1 and the maximum value is going to be 71. So you get that for free from the theory. But you can also check this out. So you can just go from -1 less than or equal to x less than or equal to 4. I don't know why it's now calling, oh, -4 to 1. Yeah, sorry. Got that backwards. -4 to 1. There you go. So now you just look at this piece of the quadratic. Zoom out to get all of it. And so you're just looking at this part that's downward sloping. So there's no place where you have a horizontal tangent. There's no zero derivative, but you can see the top value and the smallest value. So if that helps visualize it. And the other interval that I picked was 0 to 5, so 0 less than or equal to x less than or equal to 5. Whereas here now, kind of zoom in a little bit. Here you can see you've got the two endpoints. One of them is definitely bigger. It's at the actual vertex of the parabola. And again, when you're just talking about parabolas, like maximizing, minimizing, well, come on, just find the vertex using algebra 2, and you've got the maximum or the minimum. So quadratics are kind of weird examples to use this more advanced technique on. But you can also use it for cubics, for quintics, for other polynomials. And again, you can use it for maximizing functions that aren't polynomials. So it's a very general technique, but at least this proves to you that this extreme value theorem technique with using derivatives does find for you that minimum value, that vertex. I'm also teaching algebra in the academy. So I think I'll go ahead and, just because I'm thinking about it, I'll go ahead and share some algebra knowledge with you. And this showed up in a homework problem, like finding the vertex of a quadratic. It showed up in a homework problem earlier on in the semester. It's never a bad idea to review this stuff. So like, what did we do? We found out that, what was it? The vertex was, it -2, 1? Looking at 2, -1. -1. So we found that f prime of x is equal to 0 when x is equal to 2, and the y value is -1 there. And the vertex is usually denoted by hk. It's this point right here on the parabola. And you can always rewrite your quadratic in vertex form. So this is like ax squared plus bx plus c. But you can also write it as like a times x minus h squared plus k, which in this case would be a equals 2, so 2 times x minus 2 squared, and then plus k, so plus negative 1. And there are ways that you can, I mean, there's formulas that you can write, like h is negative b over 2a, and k is f of h. So you can also figure out that vertex from those formulas. And I mean, if you want to ask me in office hours or something, I'll tell you how to derive them. It's not that difficult. So any quadratic, you can find the minimum value. You can find that absolute minimum. But it's just for more complicated functions that you really like using calculus. That is to say, looking at endpoints, looking at those critical points. But that extreme value theorem stuff we're doing does, of course, work on the more simple quadratics. So I just thought I would point out that relationship to you because it is pretty cool. Any questions or comments on that? So next thing I want to show you is the mean value theorem. I hope you watched the explainer video that does explain it pretty well. And yeah, I don't think there's necessarily a proof in the book, or maybe it's like in the appendix or something, or. But I do actually give a proof that's pretty clear. I'll sketch it here anyway. But to remind you, what we're doing, I mean, what we did last time was Rolle's theorem, where you've got a function defined on some interval from a to b, and if it had equal y values at a and b, so if it were true that f of a is equal to f of b, and the function has to be differentiable on the open interval from a to b and continuous on the closed interval, but you had something like that. So if you draw the secant line from here to here, it has zero slope. And so what Rolle's theorem is saying is that there exists a point strictly in between a and b. Here's one where the tangent's horizontal. So there exists a point C such that f prime of C is equal to 0, namely equal to the Is the sound better now?
Yes.
Yeah, sorry about that. The lavalier microphone that I use just kind of, I guess, cuts itself randomly sometimes, which is unfortunate, but it's what we've got. So if that ever happens, then just you can't hear me, but I can hear you. So if that ever happens, if you just yell out immediately, then I'll know immediately and I can reset it. So that's no big deal. Okay. So hopefully my visual cues were reasonably good, as well as the verbal ones, and that the stuff wasn't out too long. Sound wasn't out too long. So this shows us that not only is it true that the derivative of a constant is equal to 0, but it's also true that if the derivative of the function is equal to 0 on a point on an interval, then that function must be constant. So any questions or comments on that particular thing? Okay. One more application of the mean value theorem. It's going to be like a very similar argument to this, but the result is really useful and far-reaching. So I'm going to say that a function is increasing on an interval if what? If the function, looks like that. So what does that mean analytically? It means that if x less than or equal to y, let's say x less than y implies f of x is less than or equal to f of y. And be a little bit careful. Some mathematicians will say increasing means that it's strictly less than, and they'll say that like monotonically increasing means less than or equal to. I say that increasing means less than or equal to, and if I want it to be strictly less than, then I would say that f is strictly increasing. So just be like a little bit careful about those definitions, because there's different authors are going to say different things. F is decreasing if the opposite happens. So like if x less than y, then f of x is bigger than or equal to f of y. Examples of decreasing functions like f of x equals 1 over x, at least for x bigger than 0. This is a nice example of a decreasing function. You can see those y values always getting smaller. Increasing functions, e to the x or f of x equals x, functions that are strictly getting bigger. So there is a relationship between the derivative of a function and whether or not it's increasing or decreasing, and we can get that from the mean value theorem, and I want to explain that to you now. So here's what it says. So we had this theorem that said if the derivative is 0 on an interval, then it must be constant. But there's two other cases. So what if f prime of x, what if the derivative is positive on the interval from a to b? Meaning for every x in between a and b, bigger than a, less than b, it is true that the derivative at the point x is positive. So if f of x is, if the derivative of f is positive on an interval, what you can conclude is that f of x is strictly increasing. And I guess I'll go ahead, maybe I'll phrase it just so I can use the language I wrote. If the derivative is bigger than or equal to 0 on that interval, then f will be increasing on that interval. And f is increasing on the interval. So if your derivative exists and is non-negative on the open interval, then f is increasing on that closed interval, and there's the definition of increasing. And the proof of this you get from the mean value theorem. So let me show you how it works. I want to verify the definition of increasing. So how can you be increasing on an interval? So if x is less than y, f of x needs to be less than or equal to f of y. What does this have to do with the interval? I should say that x and y need to be in the interval. So again, you would want than y less than or equal to b. So I should have included that condition, so forgive me. So increasing on the interval, meaning you pick x and y in that interval, possibly the endpoints, and one less than the other, then you're also going to get f of x less than or equal to f of y. So to prove this statement, I want to verify the definition of increasing. So I want to say that if this happens, then that happens. So I can start out by saying, suppose a is less than or equal to x, is less than y, is less than or equal to b. And using the fact that this derivative is non-negative, and using the assumption that x is less than y, and bigger than or equal to a, less than or equal to b, I need to conclude that f of x is less than or equal to f of y. And so how could I possibly conclude that? Well, what I'm going to do is I'm going to look at their difference. So f of x less than or equal to f of y is the same thing as saying that f of y minus f of x is bigger than or equal to 0. So I should look at f of y minus f of x, and ultimately I want to conclude that this is bigger than or equal to 0. And let's apply the mean value theorem. So by the MVT, there exists a point C between x and y. So if I'm applying the mean value theorem to the interval from x to y, there exists a point C between x and y, such that this difference is equal to f prime of C times y minus x. And what can I say about this? I mean, so first of all, y is bigger than x, so this part is bigger than 0. And second of all, by assumption, the derivative was bigger than or equal to 0. So when you're multiplying two things together, one of them's definitely bigger than 0, the other one's bigger than or equal to 0. The result, of course, is still going to be bigger than or equal to 0. So you just bring this out to the other side. So f of y minus f of x is bigger than or equal to 0, and therefore f of y is bigger than or equal to f of x, which is the conclusion that we wanted to make. F of y is bigger than or equal to f of x. And you can also see where if I said the derivative was strictly positive, then f would be strictly increasing, because then I would have strictly bigger than 0 times strictly bigger than 0 would strictly be bigger than 0. And then I would have f of y is just straight up bigger than f of x. So that also follows. And the same thing for the other one. So I could do the proof the other way. So if f prime of x was less than or equal to 0 on that interval, then f is decreasing. on AB. Goes the same. So suppose that x is bigger than or equal to a, less than y is less than or equal to b. And now I want to show that f of y minus f of x is less than or equal to 0, right? I want to show that 0 is bigger than or equal to f of y minus f of x. And so when I do it this way, I just look at, again, f of y minus f of x. By mean value theorem, it's equal to f prime of c, which now is going to be less than or equal to 0. And now I've got y minus x is still bigger than 0, multiplied by something that's less than or equal to 0. So if it's positive number times 0, it's equal to 0. If it's positive times negative, it's equal to negative. Put that together, the result is less than or equal to 0. So now I've got f of y minus f of x less than or equal to 0, and putting that f of x to the other side, I get that f of y is less than or equal to f of x, which is the definition of decreasing. So mean value theorem is the connection that says if your derivative is positive on an interval, you're strictly increasing. If your derivative is negative on an interval, then you're strictly decreasing. And this allows us to do something that we call, so let's bring this back to extreme values. This allows us to do something that we call the first derivative test, which, and so what is it? It's a test for, what this does is it says, suppose you've identified a critical point. So suppose you've found a critical point. So you've got a differentiable function and you've identified a point where f prime of c is equal to 0. So here you are on the number line. Here's x equals c, and here's f prime of c equals 0. And suppose you're at a point where the derivative is switching from a positive to negative or from negative to positive. So for argument's sake, suppose you're switching from negative to positive. So the derivative might look like that. And so we'll say f prime of x switches from minus to plus. And what I mean by that literally is that for a small interval less than c, the derivative is negative. For a small interval bigger than c, the derivative is positive. And so this is like your schematic picture of f prime of x, right? It's 0 at the point c, it's switching from negative to positive. If you look at what does that mean for the function f of x, it means that, well, you had, let's say this is c, and so c is, here's f of, f prime of c is 0, so here's f of c. F prime of c is 0, so you have a horizontal tangent there. But it also means that you were negative for these values of x less than c, so you must be decreasing function, decreasing down to your horizontal tangent, and then you are positive for values of x bigger than c, so therefore your values must be increasing. So if your derivative is switching from negative to positive, your original function must have a local minimum at the point c. At c. So before, when we found critical points, we didn't know whether they were local maximum or local minimum. And in fact, we didn't even know that they were a local maximum or a local minimum, right? So we had this theorem, Fermat's theorem, that said if you know in advance you have a critical point, then its derivative at that point must be 0. But we've also seen examples of functions like y equals x cubed such that the derivative at a point, 0, was equal to 0, but that was neither a local minimum or a local maximum. So what happens is we need a way to take a critical point and test whether it's a local minimum or a local maximum or neither. And what we're coming to is this idea that if the derivative is switching from positive to negative, then you're going to be a local minimum. And if the derivative is switching from positive to negative, you'll end up being a local maximum. And if it's doing neither of those things, you just won't be a critical point. So let's look schematically at the other picture. So what if you had, again, f prime of c equal to 0, but now you're switching from positive to negative. So then what is f of x doing? So here's your point C, here's your value. You've got a horizontal tangent through that point. Before C, you're positive, so your function is increasing. After C, you're negative, so your function is decreasing. Locally, you have to look like this frowny face, so you must have a local maximum at the point C. So the other thing you can say is that f prime of x switches from plus to minus must have a local max. And if neither of those things happen, then you just have a critical point that's probably neither a local max or a local min. So are there any questions on the statement of that first derivative test for critical points? So let's look at maybe a couple examples on Desmos. Let's go back to this quadratic. So its derivative was 4x minus 8. So first of all, it had one critical point at x equals 2, y equals negative 1. You can see that. So, and you look at the derivative, and that's where the derivative has a 0 at x equals 2, y equals 0. And look at what the derivative is doing. So let's take values of x that are less than or equal to 2. Just to make it a little bit more clear. So while the derivative is negative, look at that. While the derivative is negative, the function is decreasing, just like promised. When the derivative is negative, the original function must be decreasing. And look, the rate of decrease is going down as the derivative is approaching 0 and switching. And so that's telling me that the derivative actually is switching from negative to positive, isn't it? So that means the original function is switching from decreasing to increasing. I accidentally deleted that. Sorry, let's bring it back. So switching from decreasing to increasing. You can see that we're decreasing. We had the horizontal tangent. We're increasing. And so first derivative test is telling us something that we already knew, that this had to be a minimum, whereas if you look at like negative 2x squared minus 8x plus 7, the derivative would now be negative 4x minus 8. Now you've got the vertex still appearing at 2 and y equals 15. And now you still got this critical point at x equals, yeah, I guess it switches to -2, yeah. So you've got this critical point at x equals -2. And that's where the derivative is equal to 0. And now the derivative is switching from positive to negative. So the original function is switching from increasing to decreasing. And therefore you've got a maximum. And of course you can see it's a maximum right there on the graph, but so this is more useful when you're not already looking at the graph. So let's take the way you would set this up. The way you would set this up on your homework or something is you're given like minus 2x squared minus 8x plus 7. You take that derivative, it's equal to minus 4x minus 8. So your c is -2 f prime of c equals 0. If you draw your number line for the derivative and put -2 here, and you test a point, so like plug in -3 to minus 4x minus 8, and you'll get a positive number. So you know that your derivative is switching from positive to negative. Maybe you plug in 0 to see -8, so you're definitely negative here, you're 0 at -2, and you become positive at -3. So you draw your number line, you're switching from positive to negative, so you know you're going from increasing to decreasing, so you know that you must be at a maximum. So you can figure out that this has to be the maximum by using this, process. Is my derivative going from plus to minus? Of course, again, if you know about quadratics, you know this negative sign means it's opening downward, so this is definitely going to be a maximum, but this will work not just for quadratics, it'll work for more general functions as well. So we're developing these tests to, expand the playground of functions in mathematics, to which we can apply, our theory too. So thank you everybody for your time and attention. That's all for today, and I'll see you on Friday.
Thank you.